words. All right, so yeah, just play whatever.
I'm Luke, working with my colleague Erik. We have built Oatlog, an eGraph engine. It is notable in two ways. It is compatible with the subset of the egglog language, and it's faster than egglog the engine. We will return to Oatlog shortly, but first, how are eGraphs actually implemented? eGraphs, when used for equality saturation, initially contain some e-nodes, here denoted by circles, and e-classes, here denoted by boxes. Over time, our rewrite rules add new e-nodes and e-classes to the eGraph. We also find that some e-classes are equal, here denoted with the dashed edges. Of course, equal e-classes are indistinguishable, so we can perform edge contractions, making the eGraph as a whole smaller. We have shown this process by drawing a graph, but the actual workflow involves writing a theory in a domain-specific language such as egglog, into which we can insert an expression, run a few steps of e-matching, and extract and simplify the expression. From an implementation perspective, this involves an eGraph data structure, which must support adding e-nodes and e-classes, merging e-classes, as well as searching the eGraph for specific patterns. This data structure is then used in alternating rounds of e-matching the rewrite rules and mutating the eGraph based on the matches, including performing e-class merging. Let's approach the implementation in steps. For e-classes, let's represent them as integers and use union find to implement merging. Then, since e-nodes, unlike e-classes, have a fixed degree in the graph representation, we can represent e-nodes as tuples with an operator-specific length. Our third implementation challenge is e-matching, which we can solve by recursively walking from the root of the pattern. We can filter e-nodes based on the e-class they belong to, as shown in the pseudocode, avoiding an exponential slowdown as we add more nodes to our pattern, or equivalently, more nested loops. Taking these ideas together, we very roughly get egg, a very commonly used eGraph engine. It is relatively simple and easy to modify, but it is not the fastest eGraph engine on offer. Egg's performance is limited by its e-matching. The loop structure implementing this pattern, which appears in the distributive law, is suboptimal. If mul x has many iterations while mul y has 0, then placing the loops in this order is a serious mistake. Even more clearly, we don't use our knowledge of C1 while getting mul y, leading to unnecessary iterations. Both of these problems can be fixed with a different loop structure, with earlier checks and using all known variables wherever possible in lookups. There are many ways of arranging these nested loops to implement the pattern, and finding the best one is not obvious. A structured perspective on this problem is to view the query as a conjunctive join, turning the problem of finding a good loop structure into relational query planning. This allows us to apply worst-case optimal join algorithms, significantly improving upon top-down e-matching. Again, what did this actually mean? Our pattern trees can be turned into joins by naming the intermediate values, and we are no longer constrained to match the pattern from the root. We store our e-node tuples as rows in operator-specific tables. Joins combine rows from multiple relations based on having common values for specific columns. At this point, our eGraph is essentially a relational database, and we may look to that field for inspiration. Fast eGraph engines have to be fast database engines. Like how we filtered e-nodes by output e-class in top-down e-matching, our joins are not implemented as Cartesian products followed by filtering. Joins can be implemented using sorted data or with hash maps, finding rows with some known column values in logarithmic or constant time. Finally, our relational representation of rewrite patterns allow us to apply semi-naive evaluation, which essentially allows incremental e-matching. In the simpler naive evaluation, All results of an e-matching step will also be matched in all subsequent e-matching steps, which is especially inefficient when performing many steps on a large but only slowly growing e-graph. Semi-naive evaluation addresses this by splitting queries into many variants, each of which require one of their atoms to be among the recently added ones. While resulting in more queries, they match fewer times in total, making semi-naive evaluation a significant benefit overall. Implementing relational e-matching and semi-naive evaluation together, we would basically get egglog. And egglog is significantly faster than egg. This wraps up our background on eGraph implementation, and we are ready to focus on Oatlog itself. Oatlog is architected as an ahead-of-time compiler, allowing new tricks based on whole theory preprocessing and optimizations between multiple rewrite rules. It is algorithmically similar to egglog, using relational e-matching with worst-case optimal joins and semi-naive evaluation. Concretely, Oatlog is a Rust proc macro, embedding an equality saturation theory into your application. It implements the core of the egglog language, including primitive types and merge expressions. And above all, Oatlog achieves significantly faster e-matching and rebuilding compared to egglog. Using Oatlog involves specifying an egglog theory in a proc macro invocation or in a separate file, during which compilation generates Rust code representing the theory. Although initial expressions and run commands can be specified in the egglog source, applications will reasonably prefer to feed it through the Rust API. This is especially efficient for large input expressions compared to generating large egglog files. Oatlog supports both compilation in a strict mode, which is step-by-step compatible with egglog, and a relaxed mode, which finds more rewrites in every iteration and therefore matches egglog only after saturation. Finally, we would like to underscore how generating Rust code aids understanding, prototyping, and debugging Oatlog. You and me are already used to working with source code in general-purpose programming languages, and although the compiler part of Oatlog is at times messy, the generated code is more concrete and simpler than interpreter source code. Now, onto our benchmarks. As is evident from the abundant green on this slide, Oatlog achieves speedups over egglog across all benchmarks. The scenarios are math, which is taken from the egglog paper, Boolean adder, which performs rewrites on a 10-bit ripple carry adder, and fueled math, which is the math benchmark modified to prevent deeply nested integration by parts causing non-termination. As a disclaimer, note that this measures just the time spent building the eGraph and not extraction. The 13th step of the two combinatorially exploding benchmarks leads to out of memory on a machine with 128 gigabytes of memory. So Oatlog really does provide speedups across the entire range of reasonable input sizes, although especially for small eGraphs, where it is more efficiently using CPU cache while also avoiding egglog's startup overhead. You may notice that these figures look different from those we had in the extended abstract submitted 2 months ago. Oatlog itself was something we began working on 5 months ago, so we have been able to pick a lot of low-hanging fruit, essentially even up until today. So why is Oatlog faster than egglog? One might think that compilers are just inherently faster than interpreters, but it is not that simple. We don't really know because we lack an expert understanding of egglog, but we can identify a combination of plausible factors. First, Oatlog both avoids interpreter overhead at runtime and sends along more specific code to LLVM, which is easier to compile compared to generic interpreter source code. Second, Oatlog uses indexes that are different from egglog. Oatlog performs all index lookups in only a single hashmap lookup, although this requires more indexes and more memory for each. Egglog uses column-oriented lazy tries, which are conceptually nested hash maps, sometimes requiring multiple lookups, although with the benefit of fewer indexes and less memory for each. Third, the ahead-of-time architecture allows novel optimizations that we will discuss shortly. Finally, we have spent a lot of time performance engineering Oatlog, which has led to a steady stream of incremental gains. The first of Oatlog's novel optimizations is try-query planning. This is based on the observation that theories with many rules often have overlapping query prefixes, motivating merging the for loops into a try. This transformation is performed at the same time as worst-case optimal query planning, and it is an example of how one can exploit the knowledge of all rewrite rules before starting to execute any of them. Second, some rules provide permutation symmetries within single relations. In particular, there are often rules making operators such as addition and multiplication commutative. Inserting all permutations eagerly, whenever one is inserted, means permuting the columns leaves the relation invariant. This can be exploited for query planning. Many rules, including the distributive law, have symmetries. In this example, swapping x and y, as done by the invariant permutation, leaves the rule identical modulo variable renaming. This has consequences for semi-naive evaluation, in which we produce multiple variants of queries. In this example, the symmetry leads to one of the semi-naive variants matching a superset of another, meaning we can drop one, in some cases greatly reducing the cost of e-matching overall. Additionally, the invariant permutation means that some indexes would be equivalent, and as it can simply alias one for the other, Oatlog avoids storing and maintaining both. While we have focused on Oatlog's strengths, there are also limitations. Oatlog fails much of the egglog test suite due to missing features such as rule sets and containers. There is nothing conceptually or architecturally preventing Oatlog from implementing these, but we have simply prioritized the performance of the core language. Other features, such as extraction, are available only through the Rust API, not through the egglog code, to suit the embedded rather than interactive use case. Oatlog, as an ahead-of-time compiler, has different priorities from egglog as an interpreter, with many second compile times making it more suitable for applications with a fixed set of rewrite rules, rather than with dynamic ones or in REPLs. Finally, Oatlog's tree extraction is not optimized or benchmarked, as we have up to this point focused on eGraph building. A reasonable question to ask is to what extent Oatlog's ideas can be implemented in egglog proper. While this is in principle largely possible, there are two hurdles. The first is that this requires whole rule set query planning and optimization, possibly interfering with the ability to add and run rewrite rules in an ad hoc manner. Secondly, and perhaps on a more fundamental level, doing optimizations requires relaxed semantics. One example of this is egglog's non-deterministic mode, which allows building eGraphs that are correct only after eClass ID renaming. Oatlog's strict mode inherits this same relaxation, additionally not guaranteeing anything about the order in which rules are matched in a single step. This relaxation is typically observable only in the presence of a merge expression, which is not part of a mathematical semilattice. Finally, the invariant permutation optimizations effectively execute the commutativity rewrite eagerly, triggering e-matches earlier. This causes even the number of e-nodes in the eGraph to diverge from egglog, up until saturation, where the eGraph again is uniquely determined, modulo the previously discussed relaxations. As the eGraph only matches egglog upon saturation, invariant permutations are only enabled in Oatlog's relaxed mode. This brings us to the end of our presentation. Oatlog itself is accessible on GitHub at the following link. We built Oatlog as our master's thesis, which is titled Oatlog, a high-performance eGraph engine, and will be published soon.
Okay, great.
Hello.
Hello, we can hear you.
Yes, perfect.
Thank you for the great presentation. Hopefully we have some questions from the audience. Okay, here we are.
Hi there. That was a really awesome talk. Thank you. I'm wondering about a situation where I know some of the rules that are fixed ahead of time and some of them are dynamic. And I'm curious if you have any thoughts where maybe we could like compile that initial set of rules and then switch to something like egglog dynamically later.
So, like, it's entirely possible. It's engineering effort. I think the largest issue with that is that we decide what indexes to keep statically. Although that decision is very simple, given that we don't use tri-indices, we use flat indices. So, like, it means writing a bunch of extra code in Oatlog, the source code in the compiler to support that, but it's in principle nothing preventing it.
I have a quick question while I make over to the next question asker. As you stated in your slides, an eGraph engine, especially a sort of egglog style eGraph engine, is of course a database, and you implemented a high performance one. And so that maybe naturally begs the question, have you considered comparing against other just data log engines? There are other, code generation is a pretty relatively more standard technique over there in database world, and so that could be a interesting way to do sort of apples for apples comparison. Is this something you've looked at?
So we have not.
Well, a tiny bit, and like the main difference is for data log engines, you never remove anything. So like fundamentally, you can have like the indices always grow. So then you like really simplify your problem.
Yes. And then in terms of the problem is really quite similar, then we're doing very similar things. We just haven't compared against the concrete things. It's also a question of like all of our benchmarks are written in egglog. So it's super convenient for us to compare against egglog and inconvenient to compare against anything else.
Thanks. We have some more questions over here.
This is not quite a question, but we would love to test out Oatlog in Herbie. I think it would be a lot of fun, and we have a version that works on egglog, so it probably wouldn't be that difficult. And for others, we have hosted some prior eGraph optimization projects, and we'd be happy to host more. So if you want to test your eGraph engine or similar on Herbie, DM me. I would love to get you involved.
Yes, and you're the one who wrote in the chat, right? Yeah, I'm taking that as a yes.
Hello. So this is very exciting work. So one thing I'm wondering is, it seems like your framework, because like in egglog, like one big headache is how you can have interactions with functions written in Rust, because like egglog is an interpreter engine, like everything is boxed, have their own like value type. I can imagine like your framework will be more flexible to these functions written in Rust, because you're basically just generating code, and this can be used by others writing Rust functions.
Yeah, absolutely. It's again engineering effort, but it's just like we want to make the line go up, and then we focus on performance and the benchmarks. But like those sorts of features are totally reasonable to add.
The other question I have is, I may miss this during the talk, but are you using a like hash join for your join algorithm?
Yes, all the joins are hash joins.
Do you think maybe like some of the speedups is from by using a hash join algorithm, which is a smaller constant factor if you are dealing with simple joins, simple queries?
I mean, egglog also uses hash tables. It's again, we don't know like all of the details of egglog, but egglog to us is like textbook generic join, while I guess we do something which is kind of free join, although we didn't realize that at the time. Yeah, like so the fact that we can do one index lookup for a task that requires 2 or 3 for egglog is a factor. Finally, as a side note, we are not convinced that like we would want to do hash joins. We would maybe want to do like SIMD and just having things sorted in the right direction, but hash joins are quite simple. So,
Thanks.
yeah.
Great talk. CodeGen's super fun. Yeah, so I feel like your approach is probably going to be harder to use from other languages other than Rust, which is like one thing that egglog offers as an interpreter. It's like easier to ship a binary that you can just make bindings to in other languages. So I wondered, do you have thoughts about like how you might go about doing that part? Like if you want to have a Python interface, you know?
Like if you write a compiler and know everything in advance, like if you have a specific set of rewrite rules and like schema, you can specify that in Rust and have some like translation layer into your Python. But like you have to like maintain your like Rust layer.
Or like presumably we could probably generate that thing. Like the fundamental restriction is that it's non-trivial to add and like it's non-trivial to add new rewrite rules at runtime. And like never mind adding new tables and stuff at runtime. But like Python bindings would be fine, probably. Just the fact that you can't do it. You would need to compile some code between changing your rewrite rules and running your thing.
Gotcha. You can't generate rules in the Python bindings, yeah.
Okay.
Where the Python bindings would need to run cargo in the background or some annoying thing.
Let's thank the speakers one more time.